Imagine you throw a ball into the air. It rises. For a few moments, it keeps moving upward, but then it starts to slow down, a little more, until eventually it stops and falls back down. It seems so obvious that we barely need to think about it. Gravity is pulling the ball back toward the ground. Now imagine something much, much bigger. Imagine the entire universe being thrown outward, galaxies moving away from one another, space itself expanding. At first, you might expect exactly the same thing. The universe would expand, but the gravity of everything in it should slow that expansion down. As time passed, the expansion should gradually lose speed. But there is a problem. That is not what is happening. The expansion of the universe is accelerating. And when astronomers realized this in the late 1990s, the discovery was not just a strange detail about the cosmos. It revealed that something was fundamentally wrong with our intuition about the fate of the universe. And the explanation was given a rather curious name: dark energy. But the interesting part is that this name can make it sound as if we know exactly what it is. We don't. Let's take a few steps back. Imagine a small explosion. Now imagine several coins being thrown away from one another. At first, they all move apart rapidly, but there is something working against that motion: gravity. Each coin attracts the others. This is an extremely simplified version of what happens with matter in the universe. Galaxies contain stars. Stars have mass. Galaxies attract other galaxies. Matter tries to pull things together. So if the universe began expanding, it would be reasonable to expect gravity to constantly work against that expansion. Not necessarily stopping the universe completely, but at least slowing the expansion down. Like a ball thrown into the air, it keeps rising, but more and more slowly. For a long time, that was the expectation. The problem is that nature decided to do something much less intuitive. When we look at the distant universe, we don't just see where galaxies are today. We also see what they looked like in the past. That's because light takes time to travel. Looking at a galaxy billions of light years away is, in a sense, looking at an ancient version of that galaxy. And that allows us to compare different moments in cosmic history. Astronomers discovered something surprising. The expansion of the universe isn't simply continuing. It has begun to accelerate. It's as if you threw the ball upward and, instead of slowing down, it started gaining speed, without some visible force pushing it. And that's where the real mystery begins. But how do we know that the universe is accelerating? That's an important question, because we can't simply place a ruler next to the universe and watch its size increase. We need an indirect way to measure it. And one of the most important tools turned out to be a specific type of stellar explosion known as a type Ia supernova. These explosions have properties that allow astronomers to estimate their intrinsic brightness, and that is extremely useful. Because by comparing how bright a supernova should actually be with how bright it appears from Earth, we can estimate its distance. Now combine that with the redshift of its light, which tells us how the universe expanded while that light was traveling toward us. This allows us to compare distance and cosmic expansion at different points in history. And that is exactly what revealed the surprise. Distant supernovae were showing that the expansion of the universe had been slower in the past than it is today. In other words, the universe began accelerating. At this point, a question becomes almost unavoidable. If gravity is pulling, what is pushing? Maybe there is some unknown kind of matter. Maybe there is a new force. Maybe our equations are wrong. Or maybe there is some property of space itself. That last possibility is particularly strange because we're used to thinking of space as a stage. Stars exist in it, galaxies exist in it, planets move through it. But what if space isn't just the stage? What if space itself has physical properties? Imagine a balloon being inflated. Draw a few dots on its surface. As the balloon expands, the dots move farther apart. The dots don't necessarily have to be traveling across the surface on their own. The surface itself is expanding. This analogy isn't a perfect representation of the universe, but it helps illustrate an important idea. The expansion of the universe is connected to space itself, and under certain conditions, the energy associated with space can affect how that expansion evolves. This is where dark energy enters the story. Perhaps you're expecting a definition. So here's the most honest version. Dark energy is the name we give to whatever is associated with the accelerated expansion of the cosmos. That is different from saying that we have discovered a mysterious substance and know exactly what it is made of. We don't. And that distinction matters. The name dark energy describes the observed effect. It does not necessarily tell us the fundamental nature of the cause. It's a little like noticing that something is pulling a curtain without knowing who is standing on the other side. You can observe the effect, but the identity of the cause remains an open question. There are several possibilities being studied. One of them is what we call the cosmological constant. In this idea, space itself has an approximately constant energy density. As the universe expands, there is more space, and this component remains present. On cosmic scales, this can lead to accelerated expansion. It's a deeply strange idea because it means that empty space isn't exactly empty. Imagine two galaxies. They are separated by an enormous amount of space. Now let the universe expand. The space between them increases. Not necessarily because one galaxy is shooting away through space like a bullet, but because the geometry of space itself is evolving. Now imagine this happening on a colossal scale. Over billions of years. If the energy responsible for the acceleration remains approximately constant, the future of the universe becomes very strange. Distant galaxies will continue moving away from us. Some will eventually become so distant that their light will no longer be able to reach us. The observable universe will, effectively, become more isolated. And there is something that makes all of this even more remarkable. When we look at the contents of the universe, ordinary matter, everything that makes up stars, planets, people, and galaxies, represents only a small fraction of the total. There is also dark matter, and there is the component we call dark energy. In other words, most of the energy content of the universe is not made of the things we directly encounter in everyday life. We live inside a small island of understanding, surrounded by phenomena that we mostly infer from their effects. But that doesn't mean science is simply in the dark. Quite the opposite. We can measure these effects with remarkable precision. We know that the universe is expanding. We know that its expansion went through a period of slowing down, and we know that, later, the expansion began accelerating. What we still don't know is the fundamental nature of whatever is producing this behavior. There is another possibility. Maybe dark energy isn't a new form of energy at all. Maybe the problem lies in the very laws we use to describe gravity on cosmological scales. This possibility is taken seriously because when we observe the universe on enormous scales, we are testing our theories under conditions very different from those found on Earth or within the solar system. Perhaps gravity needs to be modified. Perhaps the cosmological constant is correct. Perhaps dark energy changes over time. Or perhaps there's an explanation we haven't even imagined yet. And this brings us to an important conclusion. The greatest discovery about dark energy may not be an answer. It may be a question. For centuries, we have looked into the sky, trying to understand what the universe is made of. First, we realized that Earth was not at the center. Then we discovered that the sun was just one star among billions. Then we realized that our galaxy was just one among billions of galaxies. And then came an even more unsettling discovery. The universe isn't simply filled with objects. Space itself is evolving, and its expansion isn't simply continuing, it is accelerating. We gave a name to whatever seems to be behind this behavior: dark energy. But perhaps the most interesting part is precisely the fact that the name still hides a question. When we say dark energy, we aren't ending the mystery. We're giving a name to where the mystery begins.